Hello everyone. So I hope I am audible. Let's start the session. So today we are gonna see single phase induction machine, problems based on that, design problems and everything. Okay, so let us start with the problem here. Starting current in the auxiliary and main windings of a single phase machine. Single phase induction machine are 8 angle minus 30-degree amps and 8 angle minus 60-degree amps respectively. Now, voltage applied is 400 angle 0 degree. Okay. We need to find out the ratio of effective resistance of main winding. Oh, I guess my skin is not good, right? Hmm. Okay, so I guess now my skin is visible. So the problem is a starting current of the main winding as well as the auxiliary winding is given, right, for both the windings, which are 8 angle 40-degree amps and for auxiliary 8 angle minus 60-degree. Now, voltage of 400 angle 0 degree is applied, right? Now, we need to find the ratio of effective resistance of main winding to effective resistance of auxiliary winding. Yeah. Can you find it? Let us see. Now, we are given with the voltage, we are given with the current, and we know the circuit of SPIN, right? Which is here 400 angle 0 degree and main winding there will be a centrifugal switch which will help in switching the machine and disconnect the auxiliary winding when motor start running at 75% of the rated speed approximately. Okay. So now here IN will flow, main winding current, and here IA will flow. Okay. Now, with the help of that, can we calculate the impedance of main winding as well as auxiliary winding? Hmm. So let us calculate what will be the impedance of main winding. Impedance will be voltage divided by IR. Okay, Vs, V factor, which will be equal to 400 angle 0 degree, where the current flowing in main winding is given as 8 angle minus 30 degree. Okay, so what will be the value of Zn here? So Zn will be 50 angle 30 degree. Okay, now since we have calculated impedance, so I hope the distance we can calculate as well as reactance. So what will be this 50 angle 30 degree in terms of resistance? We can write in form of real as well as imaginary. So 50 cos 30, it is the real component plus j 50 sin 30, it is an imaginary component. Now we know it is written as r plus the x format. So 50 cos 30 will be root 3 by 2, 50 into root 3 by 2 plus j 50 sin 30 will be 1 by 2. So it will be 25 root 3 plus j 25 ohm. So effective resistance will be of main winding 25 root 3 ohm. Okay. Now, since we have calculated for main winding, we have to do the same thing with auxiliary winding, right? So ZA is again V by IA, and V is here 400 angle 0 divided by IA is 8 angle minus 60 degree. Okay. Now we get 50 angle minus 60 degree. And further we can calculate RA is equal to 50 cos minus 60 degree, which will be equal to 50 by 2. So it will be 25 ohm. Now XA will be 50 sin minus 60 degree will be 25 root 3 by 2 minus. Right? So since we have calculated the effective resistance of auxiliary winding as well as main winding, so we can also calculate the ratio that Rn by Ra is equal to 25 root 3 by 2, sorry, 25 root 3 divided by 25, which will be root 3. Okay, so the ratio is root 3. Fine. Any doubt here? If not, then let us move towards the second problem. (400 watt, 230 volt, 4 pole, 50 hertz, SPIM with capacitor start, induction motor, full load efficiency and power factor should not less than 0.65 and 0.62. So full load efficiency should not be less than 65% and full load power factor should not be less than 0.62. Okay. Now we can also consider this value of C naught n cos phi, C naught into efficiency into power factor is 16.5 for 16 watt per hour. Okay. So these are the data given here. Now we need to calculate the bore diameter of the motor. So what is the bore diameter? Nothing but D. So we need to calculate bore diameter of this motor. Okay. So what should be the approach here?
Sir, can we put d square L is equal to
Yes.
kilowatt
Yes. Exactly.
divided by cos C1 cos phi into NS, means
Exactly.
RPS
Yeah.
speed.
Right. Sorry. NS. Exactly. So if you know this equation, you can easily calculate this value. Kilowatt is given as 400 watt, right? So it will be 0.4. C naught n cos phi is mentioned here, 16.5 into ns is given, which is
NS is not given. We have to, I think, first of all, we have to find out synchronous speed.
synchronous speed we can calculate.
Hmm.
Ns will be 120 f by t,
Hmm.
120 into 50 by 4. So it will be 1500 rpm. Okay. And if we have to convert into rps, so it will be 1500
Divided by
divided
60, yeah.
60. Yeah. So
25.
25. So it will be 25 rps. So you can write here as 25, and this value will be, if you calculate 0.4 divided by 16.5 into 25, it is 0.969 into 10 to the power minus 3, or 0.97 into 10 to the power minus 3. Okay. So this is your d square L, right? And it will be in meter cube.
Yes.
Now we have calculated t square L. Other important information is mentioned in this question is, mm, okay, I did not mention one more important information, which is L by tau. A stack length to bore diameter ratio is also given. So L by tau is given as 0.785. So from here, we can calculate the ratio of L by D indirectly, right? Because tau is nothing but pi d by t. Okay, that is the tau is nothing but pole pitch. So in a entire circumference, how much length is taken by one pole? That is pole
Sir,
pitch here.
here P is equal to number of pairs or
Number of poles.
number of pole pairs?
No, number of poles only, not pole.
Number of poles, yeah, yeah. Okay, okay.
Yeah. here, if you calculate pi by 4d, so that is the tau p. So L could be written as 0.785 into pi by 4d. Okay. So L in terms of d we have written here. This will be second equation. This will be first equation. If we plug in the value of second equation in first, we will get d cube into L is equal to 0.785 into 0.5 by 4. So it will be 0.616. Okay. If you calculate this value, you will get 0.616 is equal to 0.97 into 10 raised to the power minus 3. Okay. Now d cube, we can write as
0.97.
so into 10 raised to the power minus 3. It is 1.57 into 10 raised to the power minus 3. So this is the value of d cube. We can calculate d. We have to take under cubic root of 1.57 into 10 raised to the power minus 3, and that will be 1.163 into 10 raised to the power minus 1. It will be 0.1163 meter. Okay, so this is the value of
Yes.
bore diameter, right?
Yes, sir.
Okay. Now, since we have calculated d, we can calculate L also directly.
Stick length.
Yeah, a stack length. And a stack length will be L is equal to 0.6160. Okay, so 0.616d 0.616 into 0.1163. So it will be around 71.6 mm. Okay. So I would recommend again you check the calculations if there are any mistakes, but this is the procedure to move ahead. Okay, any doubt here?
No, sir.
Okay, great.
Sir, in a first, just I want to ask you because just I have late 10 minutes. In the first, we have to use to find out the length of the air gap empirical formula.
In first question, actually I discussed this question as a first question. So that was the ratio of resistance of main winding to auxiliary winding. I'll discuss that question which you are asking in the later question number. Okay, is that fine?
Yes, just scroll. Just can you scroll, sir?
Yeah. So here we calculated impedance because we were given, uh, currents in main winding as well as auxiliary winding. So currents are given in this problem. So we had to calculate effective resistance. So currents and voltages are given. So we can calculate impedance, and from impedance we can calculate resistance as well as reactance. So after that, we just uh, converted from polar to Cartesian. And, okay.
Actually, I have seen one equation. So, is it
Yes.
applicable? Resistance of auxiliary winding RA
Yes.
is equal to resistance of main winding divided
Yes.
by IS upon ISM, IS upon ISM square minus 1.
Is upon is a
M,
square my okay. So what is is and what is ism? So this is the
IS, it
circuit
is,
here, right? So could you please let me know where IS will be flowing here?
Source current.
Just a second. So IS you are saying here?
Yes, sir.
Okay, IS is here, and other ISM is what?
That is in a main winding.
Okay, in the main winding. So IM you are saying IS. Okay, yeah. So could you please repeat that equation once more?
Hmm.
Please repeat that equation. So sorry, we have lost Dr. Patel here. So let us. Yeah. So yeah. So Dr. Patel, can you hear me?
Sir.
Yeah. Can you hear me now?
Yes, sir.
Okay. Okay. So could you
Yes,
please
yes.
repeat that equation for me?
Yes, sir.
Could you please repeat that equation which
Yes,
you
yes,
just?
yes, sir.
Okay.
RA, resistance of auxiliary winding,
Yes.
is equal to,
Yes.
in a numerator, resistance of main winding,
Yes.
in denominator,
Yes.
IS upon ISM whole square, not under root, sir.
Okay. Not
Yeah.
IS upon ISM
ISM whole square
minus one.
minus 1. Yes.
Okay. So let us see. IS on ISM square equal to RN by RA plus
Hmm.
IS square equal to ISM square plus ISM square RN by RA. Okay, so basically it is a power balance. That is
Yes, sir.
ISM square
Currents are
power.
given, and but yes, but in this
Okay.
equation, if you will see, there is no role of the voltage, and
Yeah, yeah.
mm,
But with the help of voltage, you can calculate IS because IS is not given here.
hmm.
So IS you can calculate with is equal to ISM plus IA.
Hmm.
To calculate. Okay, so right, IS you can calculate as ISM plus IA, right? And ISM is given 8 angle minus 30 and 8 angle
Hmm.
minus 60,
Hmm.
right? So from here you can calculate IS. Okay, now RM, yeah. So RM and RA are not given, but you need the ratio only. So I think you could manage there.
Yes. Yes,
Right,
sir.
right, right. Yeah, I think you can go ahead with this.
Hmm.
ISM square RA plus ISM square RM. Mm, I don't know, but uh, from where have you got this equation? Have you derived or from somewhere else?
Yes, sir.
Like,
I
any,
got the equation from AK Sony. Uh,
okay, okay, Swami. So you just see the derivation. Has he considered any assumption or not? Because
okay.
of a
Uh,
straightforward, it does not seem to be very accurate. But still, you just go ahead and see any
right now I
assumptions
have
are
no
made.
book because this is at a college. So tomorrow I
Okay,
will
okay.
refer that. Yes.
Sure, sure. And I'll
So
also
right
go
now we
through.
are going with method which you have described, sir. No?
Yeah, like this is very conventional method, right?
Yes,
You
sir.
are pretty
Yes.
sure that
Hmm.
impedance is nothing but voltage like current.
Hmm.
Right? Okay.
Yes, sir.
Yeah, thanks for sharing this. I'll also take a look on it.
Yes.
Okay. So let us move towards the next problem. Yeah. So 500 watt, 230 volt, four pole. Uh, Pole number is four. Okay. Do not get confused between pole and pole pairs. 50 hertz. Single phase capacitor start and uh, yeah, capacitor start. So why do we go with capacitor start for single phase induction motor? Any idea?
Yes, sir.
Why do we go with capacitor start motor?
To improve the start single phase induction motor to improve the starting torque and power factor.
Yes, exactly. So that's the exact two reasons why we use capacitor starting to improve the power factor as well as to increase the starting torque. And during running condition, why do we use capacitor? Because there will be capacitor run kind of single phase induction motor. There will be capacitor start, then other is capacitor start, capacitor run. So why is it required during running condition?
Yes, sir.
For the same reason, to improve the power factor.
Yes, that is the point. Yes, sir.
Yeah, and other thing is that if your capacitor is sufficiently high enough, your noise will be very less. So your fan will be
Hmm.
running very smoothly. So that's another
Yes.
reason to use capacitor during running conditions.
Okay, sir.
So bore diameter here it is given 120 mm. Stack length is given 90 mm. Okay. Now stator outer diameter is also given 190 mm. Okay. Now 36 slots and stated tooth width is given. Stated tooth width is 6 mm and slot depth are equal to 20 mm. flux density in a stator 2 is 1.3 Tesla, and a stacking factor is given as 0.95. Okay, we need to calculate flux per pole. Okay, so first part is calculate flux per pole. So how to proceed with such type of problem? I think the equations are derived in the lectures taught by Professor Singh. So if you recall, what is the expression of uh, that flux density in terms of tooth width?
I can't recall, sir. That is.
Okay, okay. So let us, I'm just writing the equation. So phi m is equal to BTS, flux density in tooth width into lot per pole, okay, into axial length into tooth width, okay. So this is the expression of the flux, right? Now we are given with all the values. BTS is nothing but 1.3 Tesla. NSP will be 36 slots and 4 poles. So 36 by 4. L is given 90 mm. So 90 mm we can write as 0.09. Okay. And WTS is given as how much? 6 mm. So
6
point,
m.
yeah, so point 006. Okay.
Hmm.
0.006. Okay. So if we plug in all those values, we will get the value here. How much is it? 0.3 into 9 into 0.09 into 0.006. So it is coming out to be
Hmm.
6.3 milliweber. Okay.
Yes, sir.
Ah, and but while considering that axial length, we missed one factor here. Which factor? A stack length is given as 90 mm, but we also have to consider on top of that that factor of a stacking factor,
Hmm.
isn't it? Stacking
Yes.
factor is 0.95. We
Hmm.
also have to multiply with 0.9
Yes, yes.
because 95% of only this 90 mm is the core, right?
Hmm.
Remaining is the insulation in between them.
Hmm. Hmm.
That's why we have to multiply with 0.95.
6,
So if
6.3
you
into 95. Hmm.
yeah, so you will get 6 millimeter. Okay. So
Yes.
you can visualize that because of insulations, and insulations are pretty useful and important to reduce the eddy current losses. So
Hmm.
they are necessary, but because of them, we will lose in terms of flux per
Hmm.
pole. Okay, so this is
Yes.
the flux per pole. So first part we have told flux per pole. The second part is we have to calculate the depth of the stator, depth of the stator. So what is the depth of the stator core? I hope you can visualize. The depth is nothing but,
Hmm. It.
yeah. So this is kind of your rotor and a stator, right?
Hmm.
And here you have teeth like this. So this is your depth of the
Okay.
stator core. Okay. And it is denoted in the lecture by the notation as DCS.
Hmm.
Okay.
Hmm.
So how to calculate DCS? We are given all the geometry parameters. You can see from the question. Okay.
Hmm.
So uh, from which parameters we can calculate DCS?
Outer diameter is given,
Yes.
and length is given. Stick length. That
Uh,
is
but if you are seeing, if you are visualizing this in 2D, so here a stack length will not come in the picture.
yes, not come in picture. Yes, sir. Only the
Yeah.
diameter. Yeah, outer
Yeah.
diameter. Yeah.
Outer diameter and a stator bore diameter is also mentioned, right?
Yes.
Yeah, so bore diameter is just beside the air gap.
Hmm.
So it will be touching the stator teeth.
Hmm.
So this bore diameter is mentioned as 120 mm.
Yes.
So this diameter is 120 mm.
Hmm.
Now we know this diameter is 190 mm, right? Or
Yes, 190.
190 190 mm. If we somehow calculate this width, this length, then our problem is solved or not?
70.
Yeah.
70 mm. Hmm.
This is given as, so slot depth is given 20 mm.
Hmm.
Okay, so slot depth is given 20 mm. Why it is called slot
Hmm.
depth? Why not tooth length or something else? Why slot depth? Because here after this tooth there will be another tooth, right?
Hmm.
And in between them here, this area is nothing but slot where windings are placed.
Yes, sir.
So that is why whatever the length of this teeth is equal to the length of the slot
Hmm.
or depth of the slot, whatever you want to say,
Hmm.
right? So that length is given as 20 mm. So now I think everything is sorted. We can calculate this length of a stator core diameter, a stator
Yes,
core,
TCS. Yes.
depth of the stator core, or also you can say length of the back iron or back iron width. You can say this is called as a stator back iron as well. Back iron yoke, a stator yoke, whatever you want to say, all the same. So I think now we can calculate DCS will be equal to a stator bore diameter
Hmm. That is
is 190
90
mm, right?
minus
Minus
4 die
a stator bore is 120
20.
mm,
Yeah.
okay,
Slot depth.
minus slot depth, that is 20 mm. But here we are dealing in terms of diameter, so we have to multiply with 2, isn't it? And also divide by 2. Why we have to do like that?
Okay.
Because if you go in terms of radius only, then these factors will not be there. But since you are dealing in terms of diameter,
Yes, sir. Yes, sir. Yeah. Hmm.
so then DCS, if will go as radius, so it will be 190 by 2. So 190 by 2 minus 120 by
120
2
by 2. Hmm.
minus 20.
Yes.
Okay, so like that. So I hope it is clear to you now.
Air gap we have to subtract length of air gap or
So, yeah, so length, that's the difference between a stator bore diameter. So stator
okay.
bore diameter considers the length of air gap. Here,
Hmm.
this stator teeth,
Hmm.
so from center to a stator teeth, that radius is, or that diameter is bore diameter. Okay. If it is mentioned as rotor diameter, then
Hmm.
you will have to consider the air gap. But in a stator bore diameter is given, You do not need to consider air gap
Hmm.
because it includes the
Then
air gap. Yeah.
so 80 minus 60 minus
Yes.
20. So 20.
Yeah. It will no this 20 by 2 also, so it will
Oh,
be
so 10,
15 mm.
15. Yes.
15 mm. Yes. Okay.
Okay, sir.
Now the final part is how much will be flux density in the stator back iron. So for that also one equation is there, right?
Hmm.
That is mm, flux density in a stator core, stator back core is equal to how much flux is going by the air gap, flux per pole. We have to
Hmm.
divide by 2 because if this flux will enter here, so they will move like this, isn't it?
Hmm.
So half a part will go on the left side, half a part will go on the right side. So that's why we are considering phi m by 2 into axial length into diameter of sorry this width of a stator core back iron DCS whatever we just calculated. Okay, so
Yes.
basically flux divided by area, right? And in how much area that flux is flowing. So area is nothing but I have told how to calculate cross sectional area, isn't it? In the
2 pi
direction
RL?
2 pi yeah,
No.
go ahead, what is the expression?
I think 2 pi RL by number of poles for this.
2 pi RA divided by number of poles. Okay. So that used to be, a circumferential length of the rotor,
Yeah.
right? But
Hmm.
here we are calculating in a stator back iron
Yes.
where widths are uniform. So we do not need to consider only tooth width.
Hmm.
Here widths are uniform, isn't it? These
Hmm.
all area are core. Okay.
Hmm.
So area will be this width into a stack length.
Okay.
Okay.
Hmm.
And why another important trick I also have suggested, let's see in which path the flux is going or flux is flowing. Take all orthogonal two components in the calculation of area, right? So here
Hmm.
flux is flowing in this fashion, isn't it?
Hmm.
So you take one length is this and one is axial. So these two are orthogonal. So that will be helpful in considering the area. Why we do like that? Because whatever the path this flux is following, that will be considered as the length.
Hmm.
Okay,
Hmm.
so orthogonal to the length of that path will be corresponding to the area components. Okay, so this equation would not work here.
Hmm.
So that's why
Yes.
this would be useful in calculating the flux density in tooth, right?
Hmm.
So here we can calculate further. So phi m have we calculated? Phi m, yes, 6 milliweber we have found.
Yes.
So flux per pole is 6 milliweber. Where 2 into axial length is again 90 mm, I guess. Into 0.95 we have to do.
90.
Uh,
Yes. Yes.
yeah, axial length is 90 into 0.95 because of a stacking factor.
Into 15. Hmm.
Into DCS, just now we calculated a stator back iron length is 15 mm. Okay, so we
Hmm.
can calculate this value.
Yes, sir. This 6 milli paper we have to keep. Is it 6 milli or we have to convert? No?
Yeah,
Yeah.
If you are calculating in terms of a standard MLT, then you have to convert.
Now I am not keeping this.
Okay, okay. So let me calculate it for you. So 6 into 10 power minus 3 divided by 2 into 0.95 into 90 into 15 into 10 to the power minus 6. Okay. If you calculate, you will get the
Hmm.
value equal to 2.2 Tesla. So the flux density in the stator back iron is 2.2 Tesla.
Hmm. Yes.
So what kind of value is this? Can you comment anything on this value?
Just
Is it
door close करना.
is it oversaturated, undersaturated, or normal value? Because 1.8 Tesla is the normal saturation limit in typical material,
Hmm.
CRNGO, whichever you are using. And if you are going for single phase induction machine, I don't think you are going to use a very expensive material. So 1.8 Tesla is far enough to saturate the core, and 2.2 Tesla is way higher. It will
Okay.
draw so much excessive magnetizing current. So that will result into losses of the machine. So that is why this value is higher.
Hmm.
So we have to reduce, as a designer, we have to reduce this value. So what will you do to reduce this value?
Redesign the dimensions so we can say.
So what one thing you would like to change immediately?
Okay.
And let us suppose you have constraint on axial length. So from this
Can we
equation,
change this? Yes. DCS.
we can change DCS, right? We can increase the stator back angle.
Hmm.
If you increase it up appropriately, you can bring it down well below 1.8 Tesla. But
Hmm.
that will lead to higher dimensions of your muscle or higher volume of muscle. Okay,
Yes.
so we have to trade off. We have to live with it one or another.
Hmm.
But that's how if you really want to compensate on losses, that's one way to go ahead. Okay.
Yes.
Okay, great. So that's about it. Any doubt in this whole part? Third question. Okay, so I'm considering it as no doubt. Now moving towards the fourth problem which you were asking, that how much will be the approximate air gap length of a 4-pole single phase induction motor having rotor diameter equal to 120 mm. How much will be the air gap length? So Dr. Krishna Patel, do you have any expression for the air gap? I think you
Equal,
are on mute.
LG is equal to
Yes,
0.007
exactly. Yes. 0.007
into rotor diameter
into rotor diameter
under root P.
divided by under root P.
P. Where
Exactly.
this P is a number of pole pairs.
Yeah, exactly. So this P number of pole pairs. So we can write P is equal to P by 2. Right? So this were the one you were asking, right? In the beginning.
Yes.
Oh no 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 no. Sorry sorry sorry. This is exactly number four. What pole phase? Okay.
Yes, sir.
So now if we calculate it, 0.42 mm is the gap you can keep for this machine.
Yes, sir.
Okay. Let us move towards the next problem.
Mm,
Any doubt?
nice. And the second thing is that regarding one that is, I think, generally what we are keeping the number of turns between auxiliary winding and the main winding should be less than one ratio of auxiliary
Okay.
winding, number of
Yeah,
turns
yeah.
of the,
Auxiliary windings are less than main winding. Yes, yes,
and generally
correct.
we are keeping between zero point 0.5 to zero point 0.8. No?
Exactly. Yes, yes, right.
And sir, in the question, I have a doubt in 1 minute. Yes, that is a question number 6. The table is given.
Okay. Let me just go to the question number six of current week's assignment, right?
Yeah.
Okay. Yes. Question number six. Yeah. Tables are given, right?
That the tables are given.
Yes. Yes. So what is the doubt exactly there?
First, outer stator core diameter.
Okay. Outer stator core diameter, right? So see, di by do you are given,
Mm,
isn't it? And uh, d square L you can calculate for this machine.
yes.
Okay. So
Total three
once
things: outer stator core length and the inner core, stator core diameter. Yeah.
okay. So let me see if I can take a similar problem based on that.
Hmm.
I think I should have.
L by D diameter. L by D is given, and
Yeah, L. See, for just to give idea, I can directly say d square L you can calculate. So from there, sixth part you can calculate, isn't it?
yes.
Because di by do is given, and di you can calculate based on d square L equation. D square L equation, right? In terms of power also, in terms of torque also. Power
Hmm.
divided by C naught N cos phi ns, right?
Hmm. Hmm.
Yeah. So from there you can calculate that. After that, core length you have to calculate, and for that, length to bore diameter ratio is given.
But sir, efficiency is not gear. Uh,
Efficiency is not given, is it?
hmm.
Output power is given, right? And input power you can't calculate here. I think you can calculate. Let me see. I think type factor will come in the picture when you go ahead. Type
Hmm.
factor is given, right? What is the relation of type factor with input voltage?
Is it power factor? No.
No, no, it is
Ratio.
type factor. If you see the lecture there, you will see this relationship. Let me. Mm, okay, so let me write it for you. So d square L will be nothing but six, one equation is derived there, which is nothing but 16.5 C naught into this horsepower divided by N into Kf frequency factor into Kt type factor into 10 to the
Okay.
power 6. Have you seen this expression?
Uh, maybe, sir, but I have not referred this equation. Sorry.
Okay,
Yes, sir.
okay, no problem. So you just go through it and you will be able to see that what are the type factors, what are the frequency factors, and how they come
Yes.
in the picture. Okay, so this is the equation for d square L.
Hmm. So here we have to take RPM na in this equation. In
In
yes,
this equation, you in N you have to take RPM. Yes.
yes, sir.
Okay.
Yes, sir.
So I hope with this equation you will be able to calculate d square L,
Yes, sir.
and rest is just a cakewalk, isn't it?
Yes, sir.
Okay.
Then stake length we can calculate, and the last diameter. Mm,
Yeah.
that is also, I think, yes.
Yeah. Yeah. After that,
Mm,
everything is pretty. Uh,
mm,
L is given as 0.3D, right? And
yeah.
yeah, one more equation you will be required. That outer stator diameter ratio is again derived in terms of d square L in terms of outer diameter ratio. So if you recall this equation, d naught is equal to this d naught square L divided by L by d naught. And here d naught is nothing but stator diameter, stator outer diameter. Okay. So here from here, I think you can now calculate everything. L by D is given, right? You have three equations. L by D is also given as 0.3. So you have three equations and I think three unknown. And here also denote a square L. Okay. Do not confuse it with inner bore diameter. It is outer diameter. Okay. So these three equations will be enough, more than enough
Yes,
to
sir.
solve
Clear.
this. Yeah.
Mm, yes. Okay. Now 1 minute, sir. Then question number 19 is, I think, approximately like a 4-5.
Question number 9, 10 is like 4, 5. Exactly. Yeah. I think it is same, exactly same. Not even like that, exactly same. The values are also same, isn't it?
Yes, sir. So in the same way we can solve. No? Yeah.
Just like today we solved na question number this one, isn't it?
Yes, sir.
Yeah. So see, values are also same. Efficiency should not be less than 65%. Power factor also should not be less than 62.62. Stack length was given. L by tau p is given. Understand?
Mm.
So I think it is exactly same.
Yes, sir.
And acha, you are saying ki is it similar to 4-5 or not? 4-5 of the current week's assignment, right?
Mm.
Let me see. Yeah, both are same. Only values are changed.
Okay.
Yeah,
Yes.
yeah. I think you
Uh,
are sorted for this week also. Any other doubt?
Nice, sir. Just scroll down for that because I have used the another way. So that is a
Okay.
question number first. Just scroll down.
Yeah. For this particular question, right?
No, no, no. That is related to the my question of resistance. Yes, sir.
Okay,
Yeah.
okay. Resistance by reactance. Okay.
So just I want to just see that. So okay.
Yeah. Anyway, I'll upload the notes on the section where you can find all the notes, right? In the drives. Drives
Mm,
are shared with you guys, right?
yes, sir.
Yeah. Yeah. But this is the way. This is very straightforward. Just you
Yes, yes.
need to calculate impedance, and impedance in terms of polar you will get, right? And after
Mm,
you can convert into real and imaginary by
yes.
cosine and sine components. So
Mm,
cosine term will be resistance and sine term will be reactance.
mm. That's it. Just. Yes, sir. Sir, I
Okay.
have a doubt in the previous assignment. One question is wrong, but
Yeah.
I
Which
will
part?
check.
Let
Yes.
me see.
It is related to the number of turns. Yes.
Co-
In the previous assignment, question number 5, find the
Question.
stator turns per phase.
Mhm. Yes.
I have written the answer 247, but the right answer is in the between range 510 to 540.
Okay. Okay. Uh, why is did I solve in the last session similar question?
Yes, sir. And we have did this and we are getting the answer which I written 247. But in the solution it shows 510
Okay.
between
And
this range.
solution is not shared with you guys, right?
Yes, I have tried two times and I'm getting the same answer 247.
247.
Yes,
Okay.
sir.
So I think you can write to them in that Google form is there, right? Q&A section.
Sir, where I have to write that I'm confused. Key where I should where is the query?
See, you go to the course, okay,
Hmm. Hmm.
and here a Q&A section is there.
1 minute, sir. Ah, yes, sir.
Go to Q&A, and
Hmm.
there you can post.
Okay. Okay, so I have to write the question, new
Uh,
conversation. In a new conversation, I have to
New
raise the
conversation,
query.
and also write that quickly share that detailed solutions because you haven't received any detailed solution yet, right?
Yeah. So
Yeah.
I have to share my solution, which I am getting the answer.
Uh, yeah, you can share also, and other way around, you can ask also, clarify also, whatever you want.
Yeah. Okay, sir. Thank you.
Okay, so let us move to the next question. Any other doubt yet?
No, no.
Okay. Good. So again, a single phase induction machine with capacitor run is mentioned. Okay. Ratings are like that 1500 watt, okay, 230 volt, 50 hertz, 4 pole. Power factor and efficiency should not be less than 0.95. Power factor should not be less than 0.95, so it should be greater than 0.95 or equal. And efficiency should be greater than equal to 80%. Okay. Value of aspect ratio should be considered so that flux density in a stator back iron, okay, should not exceed 1.4 Tesla. Okay, just in the previous questions, I discussed that higher flux density level will lead to saturation of the machine and excessive iron losses. and a stated teeth should not be higher than 1.8 kc. Okay. Number of status slots should not be higher than 36. So it should be less than 36. Okay. Permissible current density of main winding is 4 ampere per mm square for main winding. A is equal to 4 amps per mm square. Okay. You have to calculate wire gauge, in which wire gauge you will have to use. Okay. L by pole pitch is given as 1. Okay. Winding factor is given as 0.84 60 watt per RPS. Now C naught N cos phi is given 43.465. Okay. So this is all data you are provided with. You need to calculate again bore diameter D. Second part is axial length. Third part is number of turns required in the main winding. Okay. So just give it some thought how to proceed. Okay. I'll be just back in a minute. Okay, yeah. So, are you able to think of any way to solve this problem?
Yes, sir. Hmm.
Yeah. So, how to move ahead with d square L calculation, right? D square L value you can just move ahead with because we are given all the parameters. So, D and L, I don't think any issue should be there, right? D square L is nothing but power divided by C naught efficiency cos phi, right? Into RPS, right? Into RPS, isn't it?
Yes, sir.
So if you consider this, you will get how much power is given as 1500 watt. P naught in cos phi is given 43.465, and NS we have to calculate. NS is 120 into 50 divided by 4 again into 60 because this is RPS. So 15, it is
Hmm.
again 25 RPS.
1500. Ah,
Yeah.
yes.
So 1400 divided by 43.6465 into 25. Okay, so you will get this value as 1400 43.465 into 25. You will get this value as 4.15. Yeah, 4.15 and 15 into 10 raised to power minus 3. Why 10 raised to power minus 3? Because here power is written in terms of kilowatt. 1400 or 1500? 1500. Yeah, sorry, 1500.
Hmm.
So 1500, it will be 1.38. Okay, so d square value we have calculated. L by tau is mentioned as 1. Okay, and tau is again nothing but pi d by 4 because 4 is the number of poles. Okay,
Hmm.
so L will be equal to pi by 4 d. So pi by 4 divided by, so 0.785 d. This is the value of L. Now we plug in this 1 and 2. So 0.785 d cube is equal to 1.38 into 10 power minus 3. So now from here you can calculate d. D will be equal to 120 mm. Okay. And further you plug in the value of d in 2. So L will be equal to 0.785 into 120 mm. You will get 94.24. Okay, so we have calculated initial two parts. Now the third part is how many number of turns are required
In
in
main
main
winding.
winding. Yes. So how to calculate number of turns and in which equation number of turns will appear? So when you are given with the voltage, winding factor, everything, then there is one equation, V is equal to 4.44 F by N, isn't it? So for turns equation, voltage is equal to 4.44 F by N, N is number of turns. Okay. Any other factor? KW, any other factor? I don't think so. Okay, because winding factor consists of all the factors in winding. Now, here we are being asked only number of turns in main winding. Okay, so if no information is mentioned, you can consider that 95% of windings are in main winding. So generally voltage in main winding is 0.95 times of volt.
Sir, 1 minute. How we can consider 95%?
Uh, yeah, because a majority of windings are main winding and auxiliary windings have very less number of turns compared to the main winding. And in reference books and also in the lecture, professor has also mentioned that you can go ahead with the main winding voltage at 95% of the supply voltage. So it
Okay.
is an assumption. If you increase the number of turns in auxiliary winding, this will further go down.
Okay.
Okay. So it will be 0.95 into 230. That is the voltage is equal to 218.5 is equal to 4.44 of 50 hertz. How much is the flux? So flux is not given in the problems. Okay, so another parameter we had to calculate is flux. Okay. Now, to calculate flux, which parameters are provided?
Yes, sir. Done.
Yeah, which length?
हमें थोड़ी बार शांति रखो बनता है
So we can calculate flux if we know the flux density level in the tooth, right? Uh, Here in iron core, a stator core, right? Which what is SC is a stator back iron. So in a stator back iron, flux density is given as 1.4 Tesla, and a stator tooth flux density is 1.8 Tesla. So we should just go and calculate this flux in a stator teeth as well as a stator back iron. Okay. So to calculate that, first we need to calculate the width of a stator teeth, isn't it? So how much will be the width of a stator teeth? For that also expression is there and also you can derive it from geometry. So WTS, stator tooth width is nothing but pi into uh, dis, you can say, right? Pi into dis divided by number of slots or number of teeth, okay, into which other factor will come in the picture?
I yes.
Yeah, so expression of WTS in terms of uh, yeah, this factor is, I think, duct factor or something. But that factor is considered as P. Let me write the exact equation what is required here. Yeah. So the equation of flux density in the teeth is mentioned as flux divided by slots per pole into a stack length into axial length into width, tooth width. Okay. So this is the equation of flux density in the stator teeth. Right. Similarly, flux density level in the stator core was phi m divided by 2 because flux is getting divided in two parts into K stat into L into W2S. Okay. No, here WTS will not come in the picture. Depth of the or width of the yoke, DCO. Okay. So this is the equation in terms of flux. Now, uh, we are given here BTS maximum value, and I think tooth width we are not given only, right? So tooth width we can calculate, or we were calculating here. So pi into, see, how much will be the tooth width? So if it is like that, okay, this is the radius, inner radius. Now, if we have entire circumference, this circumference, okay, so this circumference will be how much? Pi into
Ah,
D is nothing but bore diameter plus this width into multiplication of 2. So 2 times slot width. So W is slot width, right? Divided by how much? Number of slots, isn't it? So that will
yes.
be 36. So this will give you the width of each slot, or which, sorry, width of each tooth. Now, we also have this one factor multiplied with it because
Hmm.
not entire slot pitch will be occupied by tooth width and slot, there will be some insulations, and for that, this factor is
We
considered
have
as
to, yes, consider the
zero point
factor.
0.3. Yes. Now, so if we further simplify, so
So,
this
sir, it is
D
not given, then we have to consider this 0.3.
zero point
Yeah.
0.3, yes, you can
Yeah.
consider it as 0.3. Now, D we have calculated 120 mm, so 0.12 we can write plus 2 times of slot depth. Slot depth is mentioned in the question. I don't think slot width is mentioned in the question here. So if it is not mentioned in the question, how to calculate it? 5, 5, 10.
Mm.
Voltage is given, one winding factor is given. So how to compare this? Outer diameter is given.
Current density, it is not nice.
Sorry. Current density is given. You are saying main winding. For main winding, current density is given. So area we can calculate from there. If we know the current in the main winding, and from area, yeah, area will be length into width. Right. Exactly. So we will take that path, but for that we need current in the main
Mm.
winding. So that current in the main winding will be approximately 95% we can consider of the total current. Yeah, I think we have to approximate in terms of 95%. Uh, see any way there. Close to nothing here. Okay. Aspect ratio is not given here. Here it is mentioned just that the aspect ratio should be considered so that this should not exceed that width, that frequency level. But generally, you will be given with the aspect ratio. And what will be the use of aspect ratio? Here, aspect ratio is not mentioned in this problem, but aspect ratio table will be given to you. I hope you remember that table in terms of lambda. And so what they did for this particular problem, they expected you that you should know this aspect ratio table. So this will be nothing but it will be varying with pole number and aspect ratio. For, for 4 pole, this is 0.6 to 1. And for 8 pole, it is 1.2 to 1.8. Okay. Now, what is this lambda? The value of lambda, do you know? It will be the relationship between or ratio between this width this length divided by this length in terms of other multiplications, which are L by D. Just give me a minute. What is that L by D? So I don't think that equation is with me also. But that if you go back and check that equation, you will get that value of lambda in terms of number of poles. So from that, if you have calculated di or d, you will be able to calculate this value. This is if you say d back iron, and this is d. Okay. So the ratio of d by d back iron, I am talking in terms of diameter. Okay. So do not get confused, please. So d by db. Okay. So the usefulness of this lambda is if you know this d and if you know the number of poles of the machine, right? Then you will be able to calculate this value of lambda, right? And then you can calculate the value of dB. And once you are able to calculate dB, then you can plug in that value here. Here, you can write pi dB directly. You do not need to calculate this 2ws because this 2ws information will not be given generally. And here by 36 into zero point 0.3. Okay. So is it confusing or have I, or am I able to explain it? Any doubt here? So with the help of this aspect ratio, you will be able to get pi dB, or sorry, this WTS. And after you got this value of WTS, you can calculate, I think, yeah, phi. So phi m will be equal to BTS is 1.4, right? BTS is here, sorry, 1.8 into slot per pole is 36 by 6 into staggering factor is 0.95. Axial length is given here. How much? Axial length is given as or we have calculated here 94.24 mm into WT. Okay, so from here you can calculate phi m if you have calculated WTS. Okay, now the next step is you can plug in this value of phi m in this voltage equation here, right? And you know the number of turns. No, sorry, number of turns we have to calculate. You know the winding factor. So let us calculate. 95% of voltage is equal to 4.44 to F into 5 into M to KW. So we are calculating here in number of turns 0.95 into 230 divided by 4.44 into frequency is 50 into flux, whatever value will come out, and KW is 1.8. Okay, so this is the way of calculation of number of turns in main winding. Okay, now let me take a problem based on aspect ratio if I have any. Let me check it. So it does not seem like I have that part of problem. But anyway, I hope you got the idea how to solve this. Okay, so do you have any final thought before winding up the session?